Okay. Application of vectors is what this podcast is about. Basically dealing with the location of an object and the speed of an object. And what we have here is the familiar vector equation of a line, where this vector describes the position vector of any general point on the line. This would be the position vector of a known point on the line, and then some t parameter multiplying by, as it turns out, some direction vector. As we will see, just the brief theoretical development on the next slide, that basically this direction vector, kind of a slope notion, deals with the velocity and its magnitude. It will be the speed of an object. So here's a couple of examples. In a few seconds we'll study the position of two drones, R1 and R2, at a particular point in time, and whether those drones actually crash into each other or not. They start off in a particular place, as you can see from these position vectors here of a known point on the line. Then they fly sort of, this is a x, y, z, so for every over x, up y, coming towards me, one, that's kind of the flow, this sort of slope-like flow. So the argument here to start off is why is the magnitude of the velocity vector equivalent to the actual speed? So let's look at just very quickly at some general vector v. Here it is here, here's its tail, here's its head, and basically there's kind of a slope notion happening here. So if you move from this point in space, whether it's 2 dimensions or 3 dimensions, to some other point in space, you're talking about some change in y as you change in x. And so basically, if you think about it in triangular terms, as you're moving from there to there, basically you're experiencing some kind of change in x with respect to time. So you're in this plane here, and there's also some change in y that's taking place with respect to time. So this would look familiar. This is the chain rule, so dy dx has been chained across dt. And so basically what we're trying to say is sort of the rise to run here, this sort of, here's the run, here's the rise. You can see here's my rise, here's my run. That's the slope of this vector here, which is also represented as dy dx. Well, if you think about Pythagoras, that this here's your sort of a squared plus b squared is equal to c squared. Take the root of both sides, so it looks like this dy dx thing would just be the square root of the sum of these squares, which is just some numerical value. Well, what is that numerical value? That slope value would actually be the length of the vector in question, hence that'll be the speed, because the vector v is defining some kind of direction, and as it turns out, the speed of that thing would just be the magnitude or length of it. So that's the background on why we have that fact. So let's look again at the position of two drones, drone 1, drone 2. These distances are in meters with respect to time in seconds, and we'll run through 4 components here, and we'll take it piece by piece. So apparently the drone r sub 2, the speed of that can be written in this sort of simplified radical form. Let's determine the values of p and q, and we'll see the rest of these as we unfold, where we were at time 0, sure that they will not meet, and then given that there's a hawk sitting on a tree branch that flies at a certain point, so let's actually show that the hawk does actually capture, as it turns out, drone 2. So first question, speed of the drone. So what we just briefly said, and you don't need to know the theory, but we do need to know that this direction vector, the magnitude of that direction vector, that represents the speed. Hence, this is communicating the magnitude or length of what I'm calling d sub 2, the direction vector, because it's drone 2. And then basically we saw previously that the square root of the x squared plus the y squared plus the z squared, that ends up being the length of that particular vector. That's root 80. better known as 4 root 5. So we've actually shown in a P root Q form that P is 4 and Q is 5. Pretty straightforward stuff. And again, your main takeaway is that the magnitude of that direction vector is what answers the question about speed. Let's determine the distance between the drones at time 0. Well, you let t be 0 in both cases. You just lose each of these on a multiplication type effect. And so basically the first drone started here and the second drone started here as so-called initial position vectors. And so if you wanted to actually find the distance between those two, you could go back and say, well, this is an XYZ ordered triple. This is also an XYZ ordered triple. And then recall that we talked about the distance formula, which in 2 space I'm circling for you right here. Well, then in 3 space we added in just this extra z component. And so the distance or length between those two at the starting point is just the difference between the x's, 6 minus 3 squared, difference between the y's, 2 minus 0 squared, 0 minus -1 squared, which is better known as 0 plus 1. You end up seeing that it's the root of 14 or 3.74 meters. There is a second method. You could actually sort of determine vector r sub 1, r sub 2, and then find the length of that vector. So you could have a think about that. Let's actually, for the first time, show that basically 2 lines in space, sort of this is on a flight path that's linear in 3-dimensional space, and the second drone is also on a flight path that's linear. We've seen previously that lines in 3 space can cross. And we did that when we had a vector, well, we had a parameter here, maybe that was s, and this one was t, and we actually solved the system. So both of these now are a function of t because t has been defined to be time. So if the drones don't meet, then there exists no single t value such that the position of the one drone actually crosses or intersects with the other. So basically we're showing that these lines do not intersect. And the way we accomplish that is very similarly to how we saw more theoretically when 2 lines do intersect. You basically just want to say, okay, does this entity here, does it actually equal this here? So let's actually try to solve and force this system to give us the same t value. And as it turns out, when you're trying to equate these two, and again, we don't have s and t like we did previously, where you had to solve any 2 of the 3 equations and then confirm it in the third one. This one's purely a function of t, and so when you equate the x's, equate the y's, and equate the z's, you end up getting some confusing results, which basically says that there's no single point in time that actually allows for all 3 of these positions in x, y, z actually hitting and colliding at the same time, so they miss each other. This system is said to be inconsistent, meaning that it's not consistent with having a solution, so there exists no particular t such that all 3 are equal. So the answer to the question of there's a hawk sitting on the branch of a tree, and basically if you let t be 0, then the hawk would be positioned at 1, 32, 20. That would say go over x of 1, go way up high to the tree of 32, come out maybe 20, in terms of it being on a branch. So it takes off and flies towards drone 2, and so let's actually determine or show that they actually collide. So it will be 5 seconds later that the flight of the hawk actually coincides or intersects with the flight of the second drone. And so basically we're then saying, okay, here is the sort of motion or linear movement of my hawk, set that equal to the linear movement or motion of my drone, and then once again, does 6 plus 0 times t equal 1 plus 1 times t? How about 2 plus 4t, that y value, when does it equal 32 minus 2t? And do the z's match up? And if you solve carefully each of these 3, you'll find that in all 3 instances, t is equal to 5, and that guarantees that exactly 5 seconds later that the hawk has captured the drone 2 in its claws. Okay? That's it. Thank you. Bye.